Welcome to this presentation on the weighted residual formulation. If you've been following along, you know that we've already done the direct formulation and we've done the minimum total potential energy formulation. If you want to go see those, feel free to go back and look at the previous videos associated in this particular playlist on my channel here. What we're going to look at today is the weighted residual formulation. It's also called the weak form, and I'll show in a moment what it's relative to when I say the weak form. But this one has a couple different methods. There's the collocation method, there's the subdomain method, and there's Glerkin's method. There are some other ones, but these are probably the more common ones. So we're going to look at these. This specific presentation, we're going to do just the setup, and then we'll go into look at each one of these in separate following presentations. So just give you a heads up where we're headed here. All right. So as we look at the basic finite element method steps, all we're going to look at today is these two steps, because for the discretization piece, we're only going to look at essentially two nodes. We're going to look at just one element, and we're going to have boundary conditions at either node, as opposed to the one we've looked at before. We had several nodes, and so the discretization piece in this one will be relatively very simple, but you can apply it to a full analysis. So the main focus will be on coming up with a shape function, assuming a function to represent the physical behavior of the element. All right, so let's look how we do that. So here's our example. We have a beam here, and we're going to have a locked point here, and we're going to have a rolling point here with some moment applied. So the boundary conditions are going to be no displacement in the y direction at x equals 0. So no displacement here. And at there's going to be no slope change at x equals L over 2. So in the middle of this beam, you can imagine this beam bending something like, bending something like this, right? Their slope here in the middle is 0. Right? So that's what their two boundary conditions are saying there. Our governing differential equation for this, if you can remember the bending moment equation, right? It's going to be EI, or the modulus times the moment of inertia, times the second derivative of y with respect to x, equals the moment at any given position along our beam here. Now, for this particular problem, we're going to say our moment's constant for all values of x. All right, but we have our governing differential equation. So let's talk about the exact solution. Let's start out with that. We still have the governing differential equation like we had from the previous slide. And that is actually the strong form. So when we talk about the weak form using the weighted residual method, this is the strong form, is the original governing differential equation. So we take that equation, we're going to do take the first derivative, or sorry, integrate with respect to x, take the first integration so we get the first constant of integration. And we're going to apply our boundary condition there that we're going to have no slope at x equals L over 2, so we can figure out that constant of integration. We integrate a second time. We come up with our second constant of integration here. And again, we apply our boundary condition of y equals 0 at x equals 0. And we come up with our the overall exact solution of the bending of our beam. So the overall deflection that we would have there. All right, so that's the exact solution. We'll come back and compare results to this in the subsequent presentations as we do the other methods. But so take note of that, and then I'll show you that again when we do the comparison. All right, so here's the overall process. We're going to start with the governing differential equation, which we have. We're going to assume a solution equation. All right, so for this case, it seems relatively simple. It's a beam and bending, but for more complex cases, we're going to have to assume what the shape may be, and again, we'll talk about that. The assumed solution equation must satisfy the initial and boundary conditions. Right, so we can't just pick any solution. We have to pick a particular solution that's useful to us. Because the assumed solution is not exact, there will be residuals, hence the name weighted residual equation. And then we're going to force those residuals, or error, to 0 at various points or intervals using the different methods. All right, so this may be a bit confusing, so if you have a chance, check some examples in other textbooks to see what their presentation is, just so you get a couple different looks at how this goes through. So we already have the governing differential equation. We are going to start now here and assume a solution equation. All right, so we're doing those two steps here. So here's our overall example. Now remember, as it bends, we're going to get this deflection down like this. Right, nice little happy face. And so what we're looking at is we're trying to find what is y. What's the deflection here in the y direction? And so for a solution equation, we want to assume something that has that particular shape. And so in this case, we're going to assume, hey, it looks kind of like a sinusoidal function. And so we'll develop this, come up with an equation where it says, okay, we're going to have the sine of pi x over L. Well, how do you come up with this, right? Why all this stuff here? Well, remember, we need our boundary conditions must work on this equation. So let's check that. At y equals 0, x equals 0. So when y equals 0, at x equals 0. So we got a, and then we'll do sine pi times 0 over L. So now we got a times sine of 0. And guess what? That's 0. All right, so that's good. We satisfy that boundary condition. All right, so that looks good. The other one is the slope is 0 when x is equal to L over 2. All right, so we're going to take the first derivative here. So dy dx is equal to a. Now we're going to pull out the pi over L, and that'll be cosine pi. X is now 0 over L. Oh, I'm sorry, not 0. Hang on. It is L over 2. All right, so the reduces to, I'm going to a pi over L cosine of, let me just get pi over 2. Oh, cosine of pi over 2. Yeah, that's equal to 0. Right, so we do satisfy both boundary conditions. So the reason for all this stuff on the inside here is so that when we do, especially the second boundary condition, that it all works out. All right, so this right here, this is our assumed solution. Everything right here, that's our assumed solution. Right, so because our assumed solution is not exact, remember, there will be residuals. All right, so we just need to do some rearranging here, and it's relatively simple. So we rearrange the governing differential equation. What we're going to do is we're going to bring both functions to one side. So we just got 0 on the one side here. Now, for exact solutions of y, the differential equation will equal 0. But if y is not exactly correct, which we know it will be in our case because it's not a sinusoidal function, there will be error or some residual r. So what happens is instead of 0, we're going to have this r over here on the left-hand side. So we're replacing that 0 by r. That's all we're doing right here. Okay. What we want to do now is clean this up a little bit. We want to develop our error function a little bit further. We can't really do much with this when we're developing our nodal equations. So we need to break that down. So that step there is we take our assumed solution, our y, is equal to a sine pi x over L. And we're going to do the first derivative and then the second derivative. Right, and now we're just going to substitute our function we just came up with, is for the second derivative, into our function, our residual function here. Right, so this is the second derivative of y with respect to x. Right, so that's our residual function. That's where we're going to stop in this presentation, because this is the kind of the introduction, the startup piece rather, the startup piece for each one of the methods. Collocation, let me just show it here. All right. So we're going to have to force it to be 0 at various points, and that's what we're going to do in the different methods. All right, force it to be 0 at various points. So the collocation method is going to do that one way, subdomain is going to do that another way, and Glerkin is going to do that even a third way. So those are what we're going to go look at in these presentations that are coming up. Another thing I want to look at is a second example. And so won't do it here. I'm going to do it all at once. So look for that presentation following the Glerkin method presentation. So if you want to skip right to that, look in the menu and go right there. Otherwise, watch the others first, the other methods, and then you'll see the example where I do all three, just in a different way.